lecture, we're gonna advance the program that we had written last time to also account for the analytical Jacobian. So just to recap, the program that we had written last time was to solve y is equal to 1 upon b exponential of b times x and x square plus y square minus 1 equal to 0. And so the Jacobian is essentially, so we arrange these equations like this: 1 by b e to the power bx naught minus x1 equal to 0 and x naught square plus x1 square minus 1 equal to 0. So the analytical Jacobian was e to the power bx naught minus 1, 2x naught and 2x1. So instead of passing the analytical Jacobian, we had asked PETSc to find out the Jacobian for us, and that was done using the SNES FD option. But now we can also pass the Jacobian. So let me copy this program and let me first save this. So it's nlin2.c. Alright, so the core of the code remains the same, but in this particular version we're gonna make some slight changes. So we're gonna make use of this context, so this application context. So we'll go ahead and define a structure. So type def struct, or yeah, type def struct, and so this defines a structure which we will call CTX, app CTX. So it stands for application context. So it is a structure which will contain, for example, in this case, the parameter b, right? So we'll go and define inside the structure double b. That's it. So it's gonna just contain the value of b. So now when we enter into the function, what we must do is first extract what this pointer will contain. Okay, so since it is of type void, we must first cast this ctx into the form app ctx. Okay, so we have to do app ctx star user, so we are casting it into this, so equal to app ctx. So where this is the typecasting step, ctx. So with the help of this, we are taking whatever is there in ctx and we're addressing it to user. So now what that means is instead of hard coding b as 2.0, we can say b is equal to user b. So whatever the user contains in its container as b is going to be assigned to b. This is a local copy which resides inside the ctx address. Okay, so in case you don't know about structs, just have a look at any C programming book. This is how you can do it. Alternately, user b is also equal to star user dot b. That is, whatever the user points to dot b, the b content of that point t. Okay, so let's not go into that at this moment. This is how you can address it, and in various codes that you will write in PETSc, this is how you can declare the constant. So now we don't need it to be a const, but yeah, we can keep it to be a const. We don't need to rewrite a lot of code. So everything else in this function remains the same. Okay, apart from this user defined business, nothing else changes. right? So now what do we have? So we have this, the function, nothing changes over here as well. So over here we need to make the ctx variable. Okay, so inside the main we must declare it. So we will write appctx user, and now we must populate what the content of user is. So user.b will be equal to 2.0, and we have defined it over here. Alternately, we could pass this from a command line argument and uh, simply use the command line interpreter, a function like a to I but for double, to cast it from a string to a float. Right? So it's as simple as that. We don't need to worry about this. But for now, let us declare it in the main. The the reason why we would like to declare it in the main is because once we've declared it in the main, we can simply pass them to the different functions. We don't need to keep changing the value in all the functions. Well, in this particular easy case, it is only one function which is making use of b. But in case you have many callbacks, you need to define b carefully inside all the different functions if you are not using this ctx object. Alright, so user.b is 2.0. That's fine. So we have created the vectors, and this is where we create this nest object. Alright, so now before solving, so once the function is set, we must also set the Jacobian. So let me show you the function reference. So it contains a very specific syntax. So PETSc error code, SNES set Jacobian, SNES SNES, mat amat, mat pmat, and PETSc error code. And that last PETSc error code points to the function that we must define, which will construct the matrices. I'll explain that in a while. And lastly, the user context. Okay, so we must maintain this same callback. So let me keep it over here. Right, so SNES set Jacobian SNES. So mat amat is the matrix which defines the Jacobian. We'll call it J. Then we have pmat, which is the preconditioner for the Jacobian. In this case, it's going to be J again because usually it is the same as amat. Okay, in case you wanted something else, we'll do it in the function itself. Then we must provide the routine, so jack funct, and finally we must provide the ctx. So in this case, it will be the address of so it will be the address of user. Similarly, in the form function, we will also pass the address of the ctx, appctx, which is user. Right, so we're passing it, we're casting it, we're making use of it. All right, so now we must define what this jack funct will be. So jack funct is a function which will help us create the matrix for the Jacobian. But before that, we must create what j is. So after vec, we will create mat j. After this, we will create the matrix. So mat create. So it will have the usual calling sequence. After mat create, there is mat set sizes. Then there is mat set from options. Then there is mat setup, and this will be j itself. And set from options will also be set to j. Set sizes. Okay, So it will create PETSc com world and we will pass the address of j. Set sizes will be to j. PETSc decide comma PETSc decide comma 2. All right. So we have to set the size to be 2 comma 2 because in our particular problem we have a 2 cross 2 Jacobian. We can hard code it, no problem. Alright, so we have created the Jacobian over here. So now all that is left is to construct this jackfunct function. So it has to be a function which has this particular callback, right? It has to be a function which has this particular callback. It is the same as this actually. I mean, almost the same as this. So PETSc error code jackfunct, alright, and it will take SNES, then it will accept, it needs a vector. Okay, let us go over here. So it needs the input x vector like over here. So vec x, it will need the Jacobian matrix, it will need the preconditioner matrix, and it will need a void star ctx. Alright, so inside this function we must first unpack the ctx like we did over here. So we can copy this and then we can assign const double b equal to user arrow b, and we can define the auxiliary array to store x. Alright, then we must also declare, oops, this has to be tabbed, yeah, and this doesn't have to be tabbed, but it's good to keep it indented. So then we must create a value vector with which we will assign the values of the matrix. Okay, this value vector is just to sort of plug in values at the desired locations, and we have done something like this in the previous programs. So we have double v4, so it's a array of size 4 which will contain the values. Lastly, we must have an integer array for rows. So row 2 is equal to, it's simply going to be row 0 comma 1, and call 2 will be again 0 comma 1. Alright, so we have declared the insertion rows and columns, and now we can simply go ahead and create the matrix. So first we must unpack what the x vector will be. So vec get array read, it will be going from x to the address of auxiliary ax, and over here v0 will be the first entry. So what is the first entry? It's e to the power bx, so that will be PETSc x real b times ax naught. Then v1 will be minus 1.0, v2 will be twice of ax0, v3 will be twice of ax1. So we have declared these 4 entries, right? So now we must insert these into the array. So how do we insert them? So it is mat set values. So now we will put these values into p because j and p are one and the same. So p comma, so we're gonna insert 2 rows, row and 2 call. So here row and call correspond to the indices where we're gonna insert, and it's packed as row fixed, column, then column, then next row, then column. So what it means is we are going to insert 2 rows at a time and 2 columns at a time, and the sequence is going to be 1 2 3 4, right? Next we have to insert which values. You have to specify the values to be inserted, so it's simply the elements of the vector v, and we will insert values. So if in case you don't remember these, this is the way you insert values into a matrix in PETSc. Once this is done, we can restore the vector. So vec restore array read x comma ampersand of ax. All right, now we can go to the matrix assembly. So mat assembly begin, it's gonna simply be p comma mat final assembly, and we're gonna copy this, paste it over here, and this is simply gonna be end. So with the help of this we assemble the matrix. And now if j is not equal to p, right, then we must also assemble the matrix j. Now remember, we are passing from the main j comma j, which means through this modification to p, whatever we have done, j is actually modified. In case j and p are distinct, we must assemble the matrix j as it is. If in case they are equal, then assembly of p is tantamount to assembly of j itself. Alright, so if j is not equal to p, this is the case where the preconditioner and the Jacobian are different. In most of the cases, it will be the same. So this line is sort of redundant. But anyway, we must have, so we will just copy these lines because it's the same lines but done for j. Right, so over here we will have j, and over here we will have j. And at the end of successful function call, we will return 0 because the output is a PETSc error code. So yeah, this particular set of lines declares how the Jacobian is analytically built, and this is the code in particular. Alright, so now that we have called it through the function, we have created the matrix, and we must finally destroy the matrix. So mat destroy ampersand of j. Alright, so set from options. Is there anything left? No, so that's pretty much it. So now we can go ahead and first edit the make file. So the make file is somewhere over here. No, it's not. Yes, it is. So we're gonna make a new target, nlen2, control H, replace with nlen2, replace, close. So we have created a new target. Let me go to the terminal, clear. So make nlen2. Let's see if we have some error. There is an error, so let's see before SNES. We have missed this semicolon. Don't make these mistakes. Alright, so now we can simply call /nlen2 with a PETSc monitor, or rather SNES monitor short. And because we have passed the Jacobian, we don't need to additionally do the -fd. So minus SNES fd. So this is using the computed Jacobian instead of the analytical Jacobian. Well, it does give the same answer, and it is expected for such a simple problem. Okay, but there is some difference. It converges slightly better than this. The fact is, it doesn't change anything in this particular case because it's a simple problem. Alright, so this is how we do it. And okay, yeah, so this is how you go about passing the Jacobian to the function. And really speaking, this is a very simple way to go about things so that if you know what the Jacobian is going to be, I mean, passing it to the function will always help you reduce the number of function evaluations that one needs to do for the Jacobian. Because in this case, you need a lot of function evaluations because you're going to loop over the entire matrix, perform a finite difference to find out the Jacobian matrix elements. But in the case of the SNES Jacobian function, you don't have to do all that. You simply get what you want in a straightforward manner. So let us now discuss where we can go with this. So let us consider a very simple one-dimensional PDE. So let us consider a reaction diffusion system. Okay, so del U del T, where U is some species, is equal to some diffusion coefficient times the Laplacian of U. In case of 1D, it's going to be del to U del x2 plus some reaction term which may depend on the local concentration plus some source term. So this is the diffusion term, this is the reaction term, and this is the source. If it's a steady state problem, then this goes to 0, and thus we can write essentially del to U del x2 plus RU plus fx equal to 0, where we have sort of absorbed this diffusion into these terms. And really speaking, it doesn't really matter what d is going to be. It's a constant. So how do we, well, it can be a function of u as well. So how do we go about solving this equation? Well, first of all, it's a boundary value problem. And in order to do a boundary value problem, we need value at 0, which is A, and value at 1, which is B. So these are the Dirichlet boundary conditions. And so let us consider a simple case where we know what the solution is going to be. This is just to sort of verify whether whatever we're doing is correct or not. So let us consider a case where there is no source but there is only reaction. So essentially we're going to cover del to u del x2 minus rho times square root of u is equal to 0. And this is a very famous example, but I've taken this example from the book of Ed Bueller from University of Alaska, and the name of the book is let me see what's the name, PETSc for partial differential equations. Alright, so it's a new book. And it's published by Siam Publications. So it's a new book, and yeah, do check it out if you're interested in building applications with the PETSc library. So I'm going to use his own example, and what I'm going to do is, or rather what we do is, we choose a solution to this, and the solution to this, we can eyeball it. It's going to be something like m times 1 plus x square, 1 plus x whole to the power 4, because two derivatives of this and one square root of this will give the same order. So u prime is going to be 4m 1 plus x cubed. U double prime is going to be 12m 1 plus x squared, and square root of u is simply going to be square root of m 1 plus x whole square. So now when you equate these two, or so what we have over here is u double prime equal to rho square root u. We have 12m 1 plus x whole square is equal to square root of m 1 plus x whole square. So this cancels out, and this gives m, and this a row over here as well. So m is gonna be 12 upon rho whole squared. So when m is this, we get the analytical solution. We have the analytical solution that u is equal to 12 upon rho whole squared 1 plus x to the power 4. Alright, so with the help of this, we can set the boundary conditions as well. So u0 is gonna be, so let us keep it as m. Yeah, let us keep it as m, because we will pass it as a user defined context later. And u1 is gonna be m times to the power 4, which is 16. Alright, so this is a test problem, so that whatever we're gonna solve, we can sort of test it out whether it is correct or not. Alright, so now how do we go about solving this using PETSc? Let us strategize it first, and in the next lecture we're gonna solve it. So what do we have? We have minus u double prime plus rho square root of u is equal to 0. This is minus uj plus 1 minus 2uj plus uj minus 1 upon delta x square plus rho square root of uj is equal to 0. Essentially, this is the equation, and if we have n number of nodes starting from 0, 1, 2, all the way to n minus 1, so we will have n equations for u0, u1, u2, all the way to u n minus 1. So we're gonna have n minus 1 equation, rather n equations for these nodes, and they're non-linear solely because of this term. And because they're non-linear, what we need to do is to assemble them and use a non-linear solver to solve it. So essentially we have f of x naught, u naught, u1, un minus 1. So this f vector is equal to 0, and this is what we started with. This is what the discussion was in the first place. Right? So what is the Jacobian gonna be? It's gonna be del f naught del x naught del f naught del x1, so on, then del f1 del x naught del f1 del x1, and so on, and all the way to del fn minus 1 del xn minus 1. All these terms are going to comprise the Jacobian. Alright, and really speaking, we want to find out u which satisfies, so whatever the role was of x over here in this problem, the same is the role of u over here. Alright, so let us first see what the equations are. So it's minus of uj plus 1 plus 2uj minus uj minus 1 plus rho, so let's call this as h, rho h square root of uj equal to 0. So this for j equal to 1 to n minus 2. Why 1 to n minus 2? Because j equal to 0 is gonna be simply u0 equal to alpha, and j equal to n minus 1 is simply going to be un minus 1 equal to beta. So these are the boundary conditions. So how is the Jacobian matrix gonna look like? So the Jacobian matrix will look something like this. So this will be del f naught del x naught, del f naught del x1, and so on. But del f naught del x naught, because the first equation is simply u naught equal to alpha. So del f naught del x, so in this case x is u, so this will be del f naught del u naught. This will be del f naught del u1 and so on. So del f naught del u naught is going to be 1. This fellow is going to be 0 because the first equation only consists of u naught. So every other term will be 0. Similarly, on the last row, this final element is going to be 1 because this equation is this. And the last term in the Jacobian is going to be del fn minus 1 by del xn minus 1. And hence it is going to be 1. All the other terms will be 0. But what about the first term? So the first, so the equation for the node with index 1, that is the second node, the equation is minus u naught plus 2u1 minus u2 plus rho square root of u1 is equal to 0. So del f1 del u0 is equal to minus 1. So this is going to be minus 1. Del f1 del u1 is going to be 2. So plus 1 upon 2 square root of u1 times rho. Alright, so this is going to be, oh, there's a h square over here as well, which I forgot to write. Yeah, so it's rho h square upon 2 square root of u1. And the third term will be del f1 del u2, which is going to be minus 1. All the other terms are going to be 0. So it is 2 plus rho h square upon 2 square root of u1 minus 1, 0. Then for the next term, this will be this. And all the way to n minus 2 row index. So what have we done? We've constructed the Jacobian, right? So then we can simply use a SNES solver to find out the steady state solution. And in the next class, we're gonna do exactly this. Until then, have a good day. Bye.